Chapter 4 looks at the skeletal muscle system. Today's lecture should be review for everybody, so I'm going to go reasonably quickly, all right? If it isn't review at any point, please let me know so that I can slow down a little bit, okay? But you should have had A&P or structural kinese to be in here, so there should be review, okay? All right, so this diagram takes a whole muscle and then goes down layer by layer, all right? And we end up with a myofibril, which is a muscle cell. So at each layer, we have a wrapping of connective tissue that holds that particular bundle together. Right. So on the outside, the connective tissue is called the epimysium. The next layer down, which bundles a fasciculi, okay, that's the perimysium. And then the next layer down, which bundles the muscle cells, is the endomysium. Okay. So the connective tissue plays an important role because it stabilizes each separate component, okay, and it will also adapt to training. So it's not just the muscle fiber itself that is adapting, the connective tissue also adapts. Right? And then where the connective tissue runs in and becomes tendon, the tendon also adapts, and the point on the bone where the tendon is attached and yanking adapts. So we see adaptation across that whole group of elements when we've got training. Right? So we come back to the idea of training specificity. That's an important principle because what is it I want to be able to train? Which muscle groups and why? Right? We need the light off. Can you see? Is that even remotely visible? Can you see it on the camera?
I think it'd be better with the light
The
off.
light off?
Yeah. Hmm.
All right, yeah, that's better. So here's my bundle of separate muscle fibers. That picture, that horizontal cut through like this, is a useful one to hold in your head as we move through this chapter because it clears up some things that get often confused. Right? So here's my muscle cells. So this level of bundle has lots and lots of muscle cells. This level of bundle has lots of these bundles, each of which has lots of muscle cells. And then I've got several of these larger bundles stuck together to create a muscle. All right, does that look familiar? Okay. So our epimysium runs together into the tendon, which attaches to the site of the bone, right? And in this diagram, they've got the indication of some blood vessels. So we've got capillaries that are running through the muscle and wrapping around the muscle cells, providing oxygen and nutrition. And we'll come back to the capillary system later, right? We kind of work up the systems in this book. Mechanically, this picture indicates an attachment for the bicep onto the, brain fart, sorry? Yes, thank you. That attachment is slightly different in everybody, right? So mechanically, it alters the angle, and so that can alter the pulling power. Right? So not that we're doing mechanics in this class, but just to show that's one of the things that can change an individual's mechanics when we're looking at taking people as individuals. Okay? And here, this is a blown up version of our previous slide. Okay, here's the fasciculi, and each of these is a separate muscle fiber. Right, so this is perimysium around here, endomysium. Right. Again, this picture will help later on, I believe. Helps me anyway. Alright, so we've made the first point already. That means that the force that the muscle can generate is transferred through the tendon to the bone and therefore moves the skeleton. So the skeleton has no way of moving on its own unless there's muscle contraction. It's also one of the things to bear in mind when we're looking at bone health, right? The more force that's being applied to the bone through muscle contraction, the stronger that bone will become and the better the bone health will be. Right? That should say endomysium. The endomysium, the level that's wrapped around the cells, helps to prevent the electrical signal for contraction spreading from one cells to another one. And that's important because your brain wants to turn on different muscle fibers within the same muscle at different times. Right? So we don't want leakage of a muscle signal for contraction from one set of fibers to another set of fibers. Sorry?
What was the word that you said?
Here, this should be endomysium. So if we go back to that previous picture, oops. Here's my endomysium that wraps up a set of muscle cells. And when the brain activates the muscle cell for contraction, it can activate different cells at different times. So the endomysium stops a signal transferring to another bundle of muscle cells. That's something that's quite different when we look at cardiac muscle later on. Right? So preventing the spread allows for better control of contraction, better control of the amount of force that's being applied at any one time. Okay. Then another thing the connective tissue does for us is it's slightly elastic. So it's a little bit like stretching an elastic band and then letting it go and letting it ping. Right? When I stretch the connective tissue, then I add power to a contraction. And we use this a lot in sport. The technical term is the stretch shortening cycle. All right? So we do a controlled elongation of the muscle, right? So if I'm going to jump, I bend my knees and I put a stretch on the quad. It also stretches the connective tissue. When I jump, I can contract the quad and add the rubber band recoil in at the same time. So I get more force production, particularly if what I do is dum-dum, right? Rather than, as you'll see when we do our vertical jumps in lat, right? If I do this and then jump, it takes a lot of the recoil away, right? But if I'm bouncing or bounding, then I'm able to add that stretch shortening cycle. If I'm throwing a ball, we stretch and throw, right? It adds power to the throw. Plyometrics as a training regime implements a stretch shortening cycle. So if you use plyometrics in your training, if you're a jumper or a sprinter, then that is using this concept in an applied way. Now, there's some argument about stretching before a power event, because some studies have indicated that if you do static stretching before a power event, it reduces power. It's a little bit, we'll come back to it, but it's a little bit equivocal. Some studies say no, some studies say yes. One of the reasons they give for it possibly affecting power is that it reduces this recoil within the connective tissue. So there's a lot of research going on about that right now, because it's obviously from a competitive event, any little edge that you can get makes a big difference. For those of us that aren't in competitive exercise, doesn't make any difference to us, right? But for competition level athletes, it can be important. Okay, anybody never seen that before? Yay, good, that makes life easier. All right, so Z line to Z line equals a sarcomere. So if you think about a muscle cell like a long line of dominoes, each domino is a sarcomere. It is the most basic level of contractile function within the muscle. And because it's capable of shortening, it's capable of producing power. Right? And this layout of the protein filaments in line with each other like this is what gives skeletal muscle a striated appearance when you look at it under a microscope. And so but some people call skeletal muscle striated muscle. Depends which resource you're looking at. Okay. So, keep the picture in your head, right? The red line is the actin protein. And one end of the actin protein attaches to the Z line. The other end sticks into the center of the sarcomere. In between the actin molecules, we have the big fat myosin protein molecule. And it has those little projections off of it, myosin heads. Right. I'm not interested in the other three proteins. That's more than we need at this level. right? The two proteins we want to concentrate on are actin and myosin. Okay? All right, so you need to keep that previous picture in your head, okay? The other three proteins are non-contractile. That's why I don't really want to spend time talking about them. But they do help to add structure to the sarcomere, okay? Because the sarcomere has to shorten and lengthen as we see the muscle shorten when we lift something up, right? So when the sarcomere shortens, then what's happening is that the actin filaments are crossing over the big fat myosin filaments that are in the middle, and they're dragging those Z lines with them as they move. And so the Z lines come closer together, the sarcomere shortens, each sarcomere is doing that, and so the whole muscle shortens. When the muscle relaxes and the sarcomere relaxes, the proteins kind of pull back to their original length. It's not a different kind of contraction. We don't lengthen the muscle. The muscle lengthens because we turn the muscle off, and the weight of the arm, for example, with gravity pulling on it, pulls the arm down and stretches the muscle back out, right? So when I do my bicep curl, I don't uncontract, I don't lengthen my muscle, I just turn off the contraction and the weight pulls it back down, okay? All right, so what specifically is happening here then? How does the actin slide across the myosin? So the actin is often called the thin filament. Think about the picture, right? It was very thin and the red line was thin in comparison to the big flat blue line. But I think you're probably trying to get ice out to the field. Really nice back in from the field.
This one really try.
Thanks. So, the actin filament is actually composed of 3 different types of protein molecules. Okay? So we have 2 lines of actin that kind of wrap around each other, one end of which is attached to our Z line, right? And the actin has the site on it for attachment of the myosin head. We'll come back to that. Tropomyosin wraps kind of around the twist of actin, and troponin sits kind of on the top there. Don't worry about the 3 different types of troponin, too much info, all right? They act as a complex, so we're just going to talk about troponin. The myosin filament, often called the thick filament, right, has several kind of pieces of protein that are grouped together. And each piece of myosin has a globular head, it's actually a double head on it. And then they have a hinge point and a tail. So they look a little bit like a tadpole. And the tails are all wrapped around each other to make the fiber, and the little heads stick up out of the fiber. All right, so now that active site on the actin is where the head of the myosin can attach and form a cross bridge. Because it's got that pivot point, this hinge, it can use ATP to move. It kind of flips, but because it's attached to the actin, as it flips, it pulls the actin with it. Right? This head is made of myosin ATPase. Remember ATPase? ATPase is the enzyme that facilitates the breakdown of ATP to release energy. Right? So we see a lot of energy use in the head flipping. And which type of ATPase, because there are several different forms, determines, or is one of the factors that determines which type of muscle fiber this is. Is it a type 1 or a type 2? If you remember back to 212, then by the time we are 1 year old, our muscle fibers are completely decided type 1, type 2. So when we're born, we only have about 15 to 20% of our muscle fibers that are not differentiated, and within that first year, that last little percentage differentiates type 1 or type 2. So this is genetically determined. I don't get to decide whether I've got lots of type 1s or lots of type 2s. Okay? All right, so type 1s used to be called slow twitch. So again, if you're doing some research and the resource that you're looking at is calling it slow twitch, it's probably a little bit out of date. You might want to find something that's more up to date. Right? So type 1s are quite slow to reach their maximum force production. So the type 1 on this graph is the orange line here. All right? So if this is time in milliseconds, it takes some time to get to its top force. All right? And that top force, as this is level of force, is not very high. Right? But the really great thing about type 1 muscle fibers is that they're really, really good at energy system number 3, at aerobic metabolism. They are very, very good at using oxygen to make ATP. Right? When I'm using oxygen to make ATP, I am not developing an acidic environment, and therefore I don't see fatigue in those muscle fibers. Right? So which kind of event would type 1 muscle fibers be really good for?
Long distance.
Mild, Miles not quite far enough, probably. Not these, not if you're good anyway. A mile for me, yes. 5K, 10K, marathon, Tour de France,
Is there a way you can
triathlon.
tell which fibers you have?
The kind of, I mean, to tell properly would take a lab and biopsies, but the tests that we'll run, the assessments that we're running in lab, give you an applied way of telling whether someone has a lot of type 1 or a lot of type 2, or if they're average. Most of us are average, right? Not you guys, I mean, you guys aren't average, but, right? Type 2s used to be called fast twitch, and they're represented on the graph by the blue line. So you can see that the amount of time it takes to reach its peak force is much shorter, and the peak force is much, much higher. All right? Remember that power is speed times force. So the faster I can contract, the more powerful I am. The problem with type 2s is that they're not so good at using oxygen. And some of them are really, really bad at using oxygen. So they get fatigued very quickly because they're working anaerobically, and once they're outside that ATP-PC system, then they're throwing out hydrogen ions, and we're getting some lactic acid, and those hydrogen ions are turning the environment acidic, and so we see fatigue very quickly in type 2 fibers. Right? But they're really good for sprinting, throwing, jumping, anything that's short, fast, powerful. Okay? They're the ones that are going to help you out the most. Yes, ma'am?
So why aren't they called fast twitch and slow twitch? Most of them are. Like what was discovered?
I should know that, shouldn't I? I don't know. When I was an undergrad, they were fast and slow twitch. By the time I got to grad school, which was a long time later, 20 years, they were no longer slow and fast, they were type 1s and type 2s. So I don't know whether it was just slow and fast were too generic, because there are different types of them, and the more they found out about that there are different levels of type 2s, for example, then maybe slow and fast just didn't fit the bill anymore. I don't know. There might be a way more technical reason than that. Dr. Barlow would know the answer to that. So, our ratio then is genetically determined, all right? An average person is 50-50, okay? So, those of us that are not good athletes, on average, are going to be 50-50, right? So, can I run a marathon? Yes. Can I run a marathon in 2 hours? No. Can I sprint 100 meters? Yes. Can I do it in under 15 seconds? Probably no. Right? So, doesn't mean I can't do it, just means I'm not very good at it, really. Right? If we look at an elite endurance athlete, okay, so a really good 10K or marathon runner, then their ratio is much more, so let's say this is type 2 and this is type 1, right? Their ratio is much more likely to be that they've got anywhere from 70 to 85% type 1s And so that leaves us 15 to 30% type 2s. In their legs at least. Right? 'Cause that's the other thing, the ratio isn't consistent around the body. Okay? So because one of the things that makes them an elite endurance runner is the level of type 1 fiber that they have. Right? If we look at elite sprinters, then not surprisingly, the picture is reversed. They're going to have anywhere from 60 to 75% type 2 in their legs. If we're looking at sprinters, throwers would have that in their arms. Right? Oh no, 65 to 77. Getting my fives in the wrong place. And so that gives us 30 to 35% type 1s. So what makes them a really, really good sprinter is the amount of power they can generate because they've got a lot of type 2 muscle fibers in their legs.
So it's 65 and 70% type 2
Yeah.
sprinter?
I suspect if you looked at Usain Bolt, he may even have more than 70. So when we train, what happens here is that if I train sprinting, I don't get more type 2 fibers. I make the type 2 fibers I have bigger and therefore stronger and more powerful. But I can't, the switch, even when you look at world-class level athletes, the switch over of type 1s into type is minimal, very small, right? Really what happens is we just train those type 2 fibers to be amazing. Or vice versa if I'm an endurance athlete. Right? Which is one of the reasons why I really, really do not like this idea that we put in children's heads that if they work hard enough they can do anything they want, because that ain't true. At least not when we're looking at motor skills. Right? You can only do what you have the ability to do. Right? I cannot, if I'm this person, I can't win a sprint race. And if I'm this person, I'm not going to win a marathon. I can run a marathon, but it's going to be hard work. And I ain't coming in anywhere near the top 50. Right? So I think, for me at least, it's one of the reasons why the work that we do in lab, trying to work out the assessments that will differentiate someone who's got lots of type 2s from someone who's got lots of type 1s, becomes important because then we can help individuals set appropriate goals. Right? Particularly children, because it's heartbreaking when you have a goal that you never achieve. Right? And sometimes you don't achieve the goal because you never had the body to get the goal in the first place. Sometimes you don't achieve the goal because you have the body and you don't work hard enough. Right? But you can work as hard as you like. If you don't have the body, you can't achieve the goal. Okay? So the book talks about several different ways of identifying or characterizing, I guess, muscle fiber types. So you'll see the terms myosin heavy chains. Don't get into that, all right? We're going to stick with our basic classification, which is type 1s and type 2s, right? But we do have more than one lot of type 2s. So we have, pardon me, we have our type 1s. So this is my most oxidative, right? This is the one that is the best at using oxygen. Then we have a type 2A, which can work aerobically but isn't great at it. And then we have type 2X, which basically can't work aerobically, but it's really, really, really powerful, right? So this is our least oxidative.
Where did they get the A and the X from?
I'm not sure. The X's used to be B's. So again, if you're looking at a resource that says type 2A's and type 2B's, it's likely to be a little older. They changed the B to an X. I'm not sure why. When you look at the book, they also talk about type 2C's and a couple of other ones. But don't get too caught up. If you find it interesting, by all means, read it and enjoy it. So they've got like a 2AX, a 2AC, but they haven't really identified those new muscle fiber types in humans. They found them in lab animals, but they haven't really identified them in humans. So I don't want to get, until we get more work that says, oh no, look, now we know that humans have another one in here and another one in here. When we know that, then we can spend time on it. But when it's animal tissue, then it's not relevant to our training programs. Okay? In my view, anyway, right? Yes,
You said type 2A are somewhat oxidative?
yes, yeah. So now when you look at that slide, that kind of cross-section, the different muscle cells can be type 1 or type 2. Right? So if you go all the way back to that very first picture and imagine that every muscle cell doesn't have to be the same type within a muscle. Okay? So I've got some type 1s, some 2As, some 2Xs, all within one bundle, and then scattered throughout all the bundles within one muscle. All right? I'm going to stop there, but I want you, on Wednesday we will do an overview of sliding filament theory. So I want you to really have a good picture in your head of that sarcomere drawing and a really good feel for the fact that when I look at the breakdown muscle picture, not every muscle cell is the same type. Right? Because then when we start looking at training and adaptation, and how the brain talks to the muscle, that becomes really important. right? If we just assume that all the muscle fibers are the same type, then what we do later on doesn't make any sense. All right, so you've got to really understand that I've got many, at least 3 that we know of right now, different fiber types scattered throughout all those bundles that we saw in the first picture. All right? Good. Those of you that took your exam already, if everybody turns up tomorrow, I will have exams to give back on Wednesday. Okay?